Exactly, and that's why I wanted to say welcome to some new people. I see we're now 101 participants, which is great.
Yeah,
And
actually 93 participants, including 8 panelists.
yes, you are correct. I see. So this is this year's microprobe workshop, recent developments and applications in earth sciences of electron probe microanalysis. And Annette will be continuing now with the third talk of the day, which is entitled Use of Standards, Quantitative Analysis, and Statistics. So Annette, you can take over.
Good. Okay, I was just in the middle of answering a question. So share screen. I think that's it. Okay, and I'll try to sort of stay in time, but there are so many things to say. And again, the important part of this is there will be certain aspects where it will be helpful for you to read up on your own time in a book or publication. There are many good review articles and books, and I will add a short document on that lists a few recommendations to the folder that will be shared with you. Okay, so X-ray quantification standards and errors. One of the big questions is, how do we go from X-ray intensities to weight percents? How do we actually get our analytical data? And I had already mentioned that usually we acquire intensities on a range of reference materials, and which ones will be in the second part of the talk. And then on our unknowns, and we know the composition of the standard for that element, hopefully. And then there are a range of matrix corrections that we need to understand a little bit, because it helps us understand our data. So X-ray intensities. So in order to get also good compositional data, we have to make sure that our X-ray intensities are acquired correctly. We have to make sure that our choices of matrix corrections are correct, or at least understand how they inform the outcome of our data, and what standards we might use in reference materials also has an impact on our analysis. So first part is, again, our X-ray intensities that we acquire. I already mentioned that one of the problems is that what we really analyze during analysis for WDS is the peak analysis. And the reason for that is, again, in order to get the spectrum, we have to move the spectrometer in contrast to an EDS detector that would acquire the entire profile. And so what we need to know is the intensities at the peak, and we need to know the intensities here at the below the peak. Of course, we can't analyze that directly. So what we usually do is we analyze here off peak at 2 positions, sometimes depending on the complexity of the X-ray spectrum, maybe even more, and use those intensities then to calculate, to interpolate the X-ray intensity here underneath the peak, so that we get the net counts. EDS quantification works a little bit different because we have the full spectrum. And in that case, usually it's more looking at peak shapes, but usually it still does a subtraction of the X-ray background. And so the quality of our background is important for the quantification of our absolute concentrations, and it becomes even more important when we have low peak to background ratios, like trace elements and light elements, where we don't have a lot of X-ray intensities to begin with. So one of the problems is that we have is that this X-ray background can be curved. Depending where we are in the spectrum, meaning at what energy, that curvature can be very pronounced. Also, depending on where we analyze on our WDS crystal, like the way the intensities work, it can have a very pronounced background curvature. And depending on what your software you're using, you may only have access to linear backgrounds and sloped backgrounds. So a lot of the vendor softwares usually only offer linear backgrounds. It really depends what not only software version you have, but what vendor. To this day, JOL only has linear and sloped. Kamika, I think, already had like exponential backgrounds. But this is one of the reasons why so many of us use the probe software, Probe for EPMA, because it gives us access to very advanced background models. And specifically, again, trace elements, light elements, this is absolutely a make or break, because obviously if we have a slope background and then apply a linear background to it, we incorrectly get the intensity of our background. And so we might oftentimes cut off a good amount of our signal, and that ruins our whole quantification. In addition, that again for trace elements, but sometimes even minor elements, it can be a problem. I will talk a little bit more about absorption. Usually we are concerned with absorption in the sample, but we can also have some absorption from the detector gases. I didn't get to talk too much about it, but we use gases, either an argon methane mix or xenon mix in our WDS detectors. And a small, and there we can find a so-called absorption edge where our intensities of the background drop quite a bit. Of course, again, if you have like real major elements, then that can be relatively negligible, but for trace elements, minor elements, it can be a real problem. Classic example is potassium, because the potassium K-alpha line is very close to that absorption edge. And so if one of my background position is here beyond the absorption edge, of course, again, I would, like, even with a complicated background model, I would now underestimate I would overestimate. I would have too low background intensity, so I would get too high absolute counts from my corrected peak counts in this case. So that can be a problem, and the way to check that is these background positions that we use. Usually we determine empirically. What I often do when I'm setting something up, I run wave scans, or specifically, I determined at one point when I came to my lab, ran just a lot of wave scans on a lot of standards materials and try to assess like where I have relatively unproblematic background positions. So I don't have to do that on each material every time, but I need to do it at least once during my analytical procedure to know that I'm good. Then also spectral interferences can be a problem. I mentioned we generate all these different X-ray lines. So even though we might only be interested in titanium K-alpha, and only want to analyze that, the titanium K-beta line, unfortunately, in this example, overlaps with the vanadium K-alpha line, and those two elements often occur together in phases like chromides. And the vanadium K-beta line also interferes with the chromium K-alpha line, and the same is true for various other elements. Another classic example is barium and titanium. So even though the WDS can resolve peaks, spectral peaks better than the EDS, these kind of interferences can still occur. And so what that would mean is, like, if I have a material with a lot of titanium and a little bit of vanadium, some of my vanadium, some of the intensities that I would analyze at this vanadium peak position would come from the vanadium, but a good amount would probably come from the titanium K-beta line. And so interference corrections are usually available in any kind of software, but again, specifically in the probe software, because it can handle these cascading interferences really well. And so what we do is we acquire the intensities in this example on we would analyze, for example, vanadium on a pure titanium material, and we would know, okay, I get that many counts from my titanium K beta line if I have that amount of titanium in my material. And so then when we go to our unknown, I know that if I have 40% titanium, I get like 20 counts that are really from the titanium. So I need to subtract them from the counts that I get of vanadium in order to then have the accurate amount of X-rays being generated from the vanadium in my material. So more standards, important to have pure standards for certain materials for these interference corrections. And so we can always deal with that in the software, but it's something that we need to take into account in order to get accurate intensities. Then we will probably hear more on the glass analysis, but certain materials can be beam sensitive. I mentioned we generate heat. But there's also subsurface charging effects. Iri Hughes, who is one of the presenters, is like the specialist on that. And this is an example for sodium loss in a glassy materials, glasses in particular, compared to minerals, like to show that depending on the analytical conditions, over the analysis time, our intensities can drop. Often, sometimes we see also an increase. And again, the X-rays intensities that we're getting are not representative of our composition then, but of the composition and whatever beam damage we have. So at times we can just modify our analytical conditions to minimize, to mitigate this problem as much as possible. Or again, in the probe software, we have like options to correct for that by tracking the change. And we will probably hear a little bit more in some of the other presentations on that. Another thing that can be important is, if you're already familiar with EDS, there are often like dead time values listed. And that can also be important in WDS. So what is dead time? It's essentially when we look at the detector input count rate, our X-rays that are coming in. Ideally, we want to count every single X-ray, and so that our detector output rate is like 1-to-1 by our, or at least proportional counters, so that we can correlate, again, our intensities and compare them against other intensities that are higher or lower directly without, and they are a correct representation of the composition that we're analyzing. However, there's something called dead time, where essentially the processor doesn't have enough time at very high throughput to really count everything. So instead of counting all 10, it might only count 8, and that would mean that we have a dead time of 20%. So in the EDS, there are like shaping factors and processing times, and we get all these different dead times. We don't have that much with WDS detectors, but it can still be a problem, specifically if you have very high intensity and very, very low intensity materials in your analysis. And specifically when we do trace elements, and we use high currents, and if we try to analyze major elements at the same time, we might get into the range of the detectors where dead time can be significant, and so our total composition would be affected by that. So classic example, like if we don't correct for dead time, we may have a situation like that where our major element standard actually is affected by the dead time. We get lower output counts out than came in, and then when we try to compare it against the trace element analysis and would not correct for it, it would just assume, again, our 1-to-1 like linear equation, and we would get incorrect abundances from it. So again, that's something where we can either try to avoid it by the beam current or other analytical settings, or we can correct in the software. Again, Donovan just and us, we just published a paper on how to correct and calibrate the dead time that actually happens in each detector, and that can be different for each WDS detector. We might get slightly different rate for each spectrometer, And so this can be also addressed in the software, but it needs to be possible to be addressed in the software. Okay, so that was intensities, what we can do in order to get accurate intensities. And then the next problem that, used to be a problem is our matrix corrections. So I had already mentioned that there is a discrepancy between the intense X-ray intensities that we generate in our samples and the emitted intensities. And if we compare standards with our unknowns, oftentimes they are not exactly the same type of materials, either because they are knowns or because they are not adequate materials that can be used as reference materials for all type of elements. And so we have to correct the change in the intensities. And thankfully, we have a pretty good understanding on the X-ray physics that happen here. So people almost instantly, when the microprobe was devised, people were thinking about how to correct that. And there are all kind of different generations and equations that are being used. And so that is something that can also then differ in the software, and it's definitely something that should be mentioned also in the method section of data, because there are certain situations where it can have a big impact and other ones where it might be negligible, but it always factors into what our absolute concentrations are. So we need them. So a very quick run through what they are. I already mentioned, so we usually refer to them to ZAF. The different letters stand for different processes or a combination of processes. And the first one is the Z. And so the mean atomic number of the material directly controls how much our electrons beam electrons penetrate, and how much our backscatter electrons and how much X-rays can come out of the materials. There are two different effects, backscattering effect and electron stopping power, and they are usually kind of thankfully opposing each other and can cancel each other, but not fully. So this is a correction factor that usually is relatively small, but can still be important, specifically if our standard is very different to our analysis, analytical material. Then the most important correction is the absorption correction, the A in the equation. And what that means is that not all of our X-rays that we generate in the sample actually get emitted. And this is what this is shown here. That's a nickel at 10 keV, and in blue are our X-rays that are being generated in the sample. And the red is really showing which ones we actually measure, and it's a smaller amount. And here on the right-hand side, this is the so-called phi rho Z curve. And it shows essentially a histogram cut through this, where again, the maximum amount of our X-rays that are being generated might be a little lower than what is actually escape. And it gives an idea like how much X-rays we actually lose to absorption. And of course, this is all kind of depth dependent, exactly where and how deep and how much happens. And then the last thing is the fluorescence correction, which usually increases our X-rays. So you might be familiar with XRF, where we, instead of using electrons, we use X-rays to generate other X-rays. The same thing applies. We generate X-rays in the sample from our electrons, and on their way passing through the samples, if they have sufficient energy, they can energize other atoms, other electrons in our material, and can produce other new X-rays. So in this example, we might have one element that has a K alpha and K beta X-ray line. The K beta has slightly higher energy, and that is sufficient to fluoresce the K alpha line. And then we should never forget that we not only have our characteristic X-rays, but also our continuum X-rays that go all the way up to high energies, and they can contribute also to the fluorescence in our material. So usually absorption lowers the X-ray intensities, fluorescence increases the X-ray intensity, and to what degree they have to be corrected then really depends on the total material and what the other elements are. Even if you say, I'm only interested in titanium, and titanium is one of 10 elements, you have to know about the other ones, other 9, in order to get a correction for an accurate results for the titanium. So just because the absorption correction is so important, let's look a little bit more what these correction methods do, because specifically in the software, there are often different options. So originally in the 60s and 70s specifically, we found correction methods, and they are usually what are sensu stricto ZAF correction methods. And so there are a range of algorithms that try to correct for Z, A, and F, and these algorithms do it separately. And in addition, it doesn't take depth so much into account where exactly an X-ray is being generated. Partially, that is also the reason for that is it's because the computing power was not as good in those days, and so it uses more simplified equations. So ZAF usually uses the so-called Philibert approximation. And the problem then is that while the true shape has X-ray emission throughout the depth of the sample, the Philibert approximation is weak when it comes to the shallow ones. Now, that is a problem then depending on the materials and the elements that you're analyzing. So usually we get very good results with ZAF for metals and steels and anything with like higher energy X-ray lines and heavy element materials. But when it comes to oxides and silicates, and specifically something like where we have to analyze the ultralight elements like carbon, nitrogen, oxygen, most of these low energy X-rays get absorbed in the deeper parts. So really most of the ones that we analyze are at this shallow level, and that's where the ZAF correction gets weak in terms of outcomes. So people then developed what we now call Phi-Rho-Z correction methods, and that takes into account the mass depth. We don't always, it doesn't know the density of the material unless we tell it. So at its basis, it's just looking at mass depth, but it's looking at what essentially depth the X-ray is being produced in the different materials, and it is a combined correction for Z and A into a single calculation. And that vastly then improves our outcomes for light elements, oxides, silicates, all that. So if we can, we usually want to use a Phi-Rho-Z correction method. They still work for like where the ZAF corrections are good. So it's usually the better choice in general. And it becomes especially important, again, if you have a combination of less energetic X-rays that are in a matrix of high energy like elements and vice versa, where absorption would be big. And so these are pretty crappy screenshots, but just to show you different softwares that I used so I could take screenshots, both for EDS software and microprobe software and the probe for EPMA one. And they all list slightly different options and ZAF and whatnot. And oftentimes people forget what actually is chosen. And in order to get consistent results, you want to stick to one. But again, sometimes you don't have access to the most modern ones, depending on the vendor. For example, when I do light element analysis, like ultralight element analysis, carbon, nitrogen, oxygen, I find I really have to use this PROSA correction that was developed specifically for these kind of elements from Bastin. And the only software that I had in my lab that would use it was the Thermo EDS, but now the Brooker doesn't have it anymore, and the probe for EPMA software, but not the JOL or Kamika one. So it can vary, and that's where some of the differences can come from. The Profo EPMA software also has a great function where I can test my data with all matrix corrections. So it crunches the numbers for an analysis and shows me to what degree I get different results. And that, again, there are certain situations where it doesn't matter so much, where all my results are very close together, but then there are other ones where it matters greatly. And so that gives me kind of a sanity check. And also plug, the probe software has a free little utility tool called CalcSAF that everyone can use, and that also allows you to play around and get an idea how much it matters, even if you don't have the function in the vendor software that you're using. At least you know how secure you can be in those numbers by using one of these modeling tools and see how much it matters. Okay, more guidelines when to know. I mean, only when you model it or try it, you know in absolute terms, but there are certain basic recommendations where things get difficult. So again, when we look at the excitation volume, we generate X-rays with a certain depth, and usually we look then at the data in terms of these phi rho z curves, where essentially along this axis is the intensity distribution and down here is depth. And so what is important to know is that there are three main parameters that affect the shape and extent and all that of the curves. And so the first thing is what kind of accelerating voltage, and that's this E0. So in general, the higher the accelerating voltage, the deeper we put our X-ray generation, and the deeper the X-rays have to, like the longer the travel path to the surface is. So if absorption is a significant problem, going to a lower accelerating voltage reduces the problem. So stuff like that can matter. Then also it depends on the particular X-ray line that you're doing, not as much with the accelerating voltage, but still it makes a difference. So again, the problem is that we can't just normalize things, because each element that we analyze is affected by that effect to a slightly different degree. And then, unfortunately, also, in addition, the mean atomic number of the material gives us different curves. So again, even if we're just interested in one element, we need to know about all the other elements. Otherwise, we can't correct for that. So there are different things that then can directly be a problem for our analysis. The first thing is charging is bad. Charging of the sample changes the accelerating voltage with which the electrons hit the sample. It often is reduced. And if we are just off by 0.1 kV in the accelerating voltage relative to what we said in the software it would be, it can have like percentage effects on our data. The other thing is we need to analyze all elements, or if we don't want to analyze all elements, we have to specify all of them. And that also, and the elements that we put in are all relevant. So the other thing is sometimes when you do EDS, elements get not correctly assigned by the software. If you run it in fully automated, it matters, even if you say, I'm not interested in this other element, if it's not part of the total output. But yeah, so even like we can't analyze hydrogen, but we want to specify it in some way, at least ballpark, how much it would be. Oftentimes we do that by difference. For elements like oxygen or carbon and carbonates, we know it's stoichiometric. Like there are ways that we know how much it is, or we know what the abundance is by a different technique that we use. But if there are no other ways, we need to try to analyze as all elements as possible. The same thing, mixed analysis are bad. So you can't do defocused beam analysis to get a bulk composition of your material, because that's not how the X-ray physics work. So that's the first thing. The second thing is, like, when you're close to a grain boundary, it might slope. And again, it's like the matrix corrections assume a homogeneous volume. So if it's not, the X-ray generation then will differ depending on if it hits the high density phase first or second. And so mixed analysis in general are just bad data. I already mentioned the defocused beam analysis, meaning like you widen the beam and pretend that this is like a bulk technique. You could do that with a laser. You can't do that with X-rays. And so these are situations when you set points and do sample prep are the reason why that is so problematic. Okay, then another important aspect can be that part of the algorithms that we use use values for the absorption correction, and those are the so-called mass attenuation or absorption coefficients. They're usually seen as an absorber-emitter pair. So this would be like vanadium and chromium would have that MAC, mass absorption coefficient. Manganese and chromium would have that, and you can see that these values can be fairly high and relatively small. If they're high, there's a lot of absorption. If they're low, there's not so much absorption. And these tables are empirical, and so certain ones are really well defined. Other ones are extrapolations where you can't have these binary materials. And so there are also some uncertainties for light elements, transition metals, and so on. And that's why there's not just one of these tabulations, but there are different ones, and they have different like dates. And so one of the problems is can be that some table can have like a real outlier. This is an example for, I think, magnesium and iron, where that can have an effect. And that's why you sometimes hear people being so adamant about matrix matching standards. It's not that it's not that we can't do it with like other non-matrix match standards. Might be that our software has a weird outlier in the table. And then finally, so we have to take all this into account to get a good analysis, but then how do we assess that it's a good analysis? And so there are like three main things that we usually do. Is one, we try that the analytical total is close to 100. What the exact cutoffs are depend on the field and group. Some people say 99 to 101. Other people say 98.5 to 100.5, because it's more likely that you didn't analyze a range of trace and minor elements that add up to 0.5%. But you should get somehow close to what seems like a complete analysis. An additional thing to look at is mineral stoichiometry. Does it make sense? Specifically, if like one element is too high and the other one is too low, your total might still look good, but the mineral stoichiometry might be a little wonky. And so if you are analyzing minerals, it is worthwhile to calculate the mineral stoichiometry. And then lastly, it's always a good idea to check reference standards, and if they come out accurate, specifically if you do like standardless EDS, but also in WDS analysis, specifically if you can't analyze mineral stoichiometry well, because yeah, you should get the published value on a material of known composition, and then you have a higher then you know that your outcome on the unknowns should be robust as well. Here, I don't expect you to read that, but the PDF will be shared. There are all kinds of spreadsheets and ways to calculate mineral stoichiometry. There's a lot of cool stuff now happening with machine learning as well. And so here, just some literature and things to look at when it comes to the stoichiometry. But still, I want to say never trust the spreadsheet. Don't use it just like you found something random on the internet. Always start out with an analysis that you know what the stoichiometry should be to test that the spreadsheet actually works. Okay, so lastly, a few words to standards and reference materials. Usually, each lab should have a relatively good collection of standard and reference materials. The more you have, the more versatile your applications can be. And again, it can be a real big part of both for checking the accuracy of your data, but also to calibrate your elements. And usually standards are like in these mounts where we have like up to 30 different materials. And but they are not all created equal. And so a few words to that and best practices. One thing that always amuses me is that also there's even a standard reference material for peanut butter. So they come in all kinds of shapes. Okay, so our choices and standards are factoring into both the intensities, the matrix corrections, and the composition. So similar to our unknown materials, we have similar requirements for our standards, which is they should be immune to oxidation, they should be stable under the vacuum and electron beam, but then in addition, they need to be homogeneous on a micrometer scale for the elements that we want to test and calibrate on. And ideally, their composition should be determined by a different suitable analytical technique. So while some people just go to the mineral collection, analyze it by microprobe and declare that now a standard, strictly speaking, it's really not. It's just an internal check reference material. We usually
10 minutes, Anette.
Okay, thank you. Usually when we talk about standards, we distinguish between calibration standards. So these are the standards that we use to calibrate the X-ray intensities on. And thanks to us being so good with matrix corrections anymore, they really don't have to be anywhere close from my perspective. Other people still feel that, but it's really not. It doesn't have to be similar to what you're actually analyzing. So, and I will go a little bit in the differences there in a moment. And then we also have reference standards, and those are usually to test if your overall analysis comes out accurate. And there it makes sense to have a material that is similar to your actual material. So while I would never use a biotite standard because then for calibration, because they're beam sensitive and they're usually not great, because the biotites tend to not be, they're not that many that are very homogeneous. So Mother Nature is with certain ones not that good. They at times can make an okay reference standard to check my biotite analysis, as an example, or glasses or something. But of course you can also use a calibration standard as a reference standard if it happens to be a similar material. But so those are the two kind of types. So they might be the same material, but they serve two different purposes. Then a few words to, I and everyone else always use a standard just as a catch-all, but when you talk to someone like at NIST, at the National Institute for Standards and Reference Materials, then they will yell at you because a standard is a very specific thing. So usually all standards are reference materials, but not all reference materials are standards. And reference material is our most generic term, and it just means that a material is sufficiently homogeneous and well established. And if you buy it from somewhere, it should come with a report of investigation, meaning like a composition. Then there's something called certified reference materials, and that is usually already a little bit less even when you buy them, that you have, and they are usually give more information, make it traceable, and specifically the certificate should should also have like certified list which values are certified and what their uncertainty is, because sometimes you buy materials and they're only certified for a few elements but not so much for the other ones, and so it's important not to treat them all elements equal just because you called it a standard, if you haven't checked what actually is the documentation for that material. And then the crown of it all are standard reference materials, which again is something that comes with a certification of analysis. It usually even includes information regarding the appropriate use of the material. And so, and oftentimes is actually the results are validated by more than one other technique. So we shouldn't call everything standards. A lot of the materials that we deal with are reference materials, and we should try to replace reference materials with proper standards if we can. There are different sources for these. I mentioned NIST. There's also some that you can get for free from the Smithsonian microbeam analysis. There are other ones that you can purchase from commercial vendors, but also the USGS. Each country usually has some kind of material analysis, like national lab, that also sells some. So there are different places, and it's worthwhile to Google and ask people and see what people use. Okay, so when it comes to, so now you want to buy some more, and what do you want to buy, and what is a useful
5 minutes,
addition?
Anette, break.
Thank you.
Sorry.
Good. Yeah, we're getting, that should work. So at its basis, there are two different broad philosophy when it comes to calibration standards, and its most basis, and it's hotly contested and discussed at times, and you know, it sometimes really depends what your specific application is, but yeah, at its basis, like you can say, oh, I just use pure elements, or I use compounds, and there are pros and cons for each. And then also there is like a faction that says I use synthetic glasses for everything, whereas other people say we analyze natural minerals, so we should use natural minerals. So let's talk about that for a second. So the advantages if you would use pure elements is usually they have very high concentrations and they tend to be very homogeneous. So that's great. But actually I usually avoid them. They can have all kinds of problems. One is like, they are not really as pure. It might not even be possible to get some of all, like what is a pure fluorine standard or pure chlorine standard. We don't have that as a solid material. And then other ones, specifically the metals, can be really prone to oxidation. Even like in seconds, you produce a oxidation layer. So they don't have the composition anymore that you thought they have. Some elements are difficult to just prepare, get a good polish on them. So that can be a problem. And of course, when it comes to matrix correction, they're like the furthest away from your material that you analyze. So you're really relying on the goodness of the matrix correction. And there comes a point where it's like getting a little bit like maybe too much trust. And in addition, I haven't really talked about it, but specifically for the light elements, the electrons that are involved in the X-ray generation are also involved in the bonding. So the actual peaks that we are measuring can change depending on the bonding. Am I in a metal, or am I in an oxide, or am I in a sulfide, and so on. And so at times we can have peak shifts. And so metals, again, if you're not in a lab that analyzes metals, they're probably the furthest and most problem prone to what you can use. But if you're in a lab that uses metals, they might be your best choice if you can keep them unoxidized. Then when it comes to synthetic compounds or natural minerals, the positive in using either is that you minimize corrections for major elements because usually they are a little bit closer to your composition. You can match the chemical state, again, oxides for oxides. Again, that only really matters then for the low energy X-rays. They still can have like if there's beam instability, they can just be like similarly affected. The problem with a lot of natural minerals and some of the synthetics is they can have small inclusions and heterogeneities. This is an example of a Smithsonian standard where you can see in the backscatter that there are some grains in there that are clearly not the main material. That can be okay because they're easy to detect. But if it's more subtle zoning or sometimes some of the population where the published value is coming from a bulk technique like wet chemistry, the grains that you're getting, if there's a little bit more heterogeneity in their population, can deviate from the published value. And sometimes we just don't have much material of, like there might be something great, but it's not, it's like out of stock by now, or you can only get very limited amounts. So that can be a real problem. And then one thing that also should be mentioned, so there's like, this is kind of from Paul Carpenter at Washington. He distinguishes good, bad, and ugly standards. Again, ideally, we want to have like excellent, characterized, ideally certified, homogeneous, inclusion-free, all that. Then not great is these in-house single primary reference material that you characterized yourself or someone else did, or they are homogeneous for some elements or have some up, or you don't even know where they come from. And then the worst is, of course, the ones that are really heterogeneous, but you can also turn good standards into ugly standards by not maintaining them properly, because they can accumulate beam damage, and because we analyze them again, but also you can just like give them a bad polish, and that then has an effect on everything. Okay, lastly, specifically as we're coming to the end, and Donovan will, I think, talk a little bit more about it, a few words to counting statistics and precision and sensitivity and what matters there. Because usually we use this technique for high precision, high accuracy data, and in EPMA, we have systematic and random errors that can affect both. And usually what we really are talking about is the measurement uncertainty. So there are certain things like counting statistics, but also other stability and how we set points that can affect the precision. And then the accuracy can be affected by bad standards, both from polish or from that they don't have the composition, or that we choose outdated matrix correction, or any of that. So that can be important. And again, I just refer to further literature that goes much better into the details there. So have a look at that. A few words to counting statistics. Again, so we get certain intensities. They are a factor of how much of the element is in the material, but also what accelerating voltage and beam current we're using. And we have to analyze it long enough to get our Poisson distribution. And our standard deviation is usually just the square root of the total counts. And so oftentimes we try to hit a specific error, a specific precision, and usually we aim for 1 sigma. And a good benchmark to know is like that we need at least 10,000 counts to get a 1% error. That then informs that what kind of beam counting time, beam current and counting time we need to choose. Again, the count time, then we have to count as long until we get 10,000 to get our 1% error. For a trace element, that takes longer than for a major element. And then we also analyze the background counting time, and what that is then informed by our peak to background ratio and what our peak counts are, and we can calculate what that number should be. So that's how we get count times for peak and background. The precision is given by these kind of equations, and I will not go too much in these. Again, what is in our detection limit, what really matters is our background. That's important, not so much our peak. The count rate on the standard and what ZAF correction we have. And likewise, our average detection limit is then, of course, a measure of, again, standards, but also the background counts on the standard. Again, that's where the peak to background really comes in. And then how many points we are analyzing. And I will also add a PDF that just collates what the different software programs use, like JOL versus Chemica versus Probe software, to calculate these, because sometimes they are actually calculated slightly different. And then again, peak to background is very important. Our background measurement becomes less important if you have a large peak to background, like when we do a major element. But then when we do a trace element, we essentially, our peak is almost as high as our background. And then usually we want to analyze our backgrounds longer, at the same amount of time or close to it as our peak counting time, because that they are as important as the peak in order to get accurate data. And that is, again, the speed run through all this effects. Again, there was a lot of information. Look at this presentation, but otherwise look at the details of the literature. And again, there are modeling programs that allow you to calculate count times that let you explore with that. And they're really useful even just to play with it, to get kind of an idea about how all these different factors go in. Okay, good. I'm over time.
Yes. It's okay. Yes, but thank you, Annette. We understand that it had to be long, this, because of the subject. So we're going to move the questions to the end of the session, because we'll have time for discussion, and also my talk will be a bit shorter, so we can manage everything, I think. So we'll leave them either unanswered, but if you want to type something, please go ahead.
Yeah.
Perfect.
Good.